Hello and welcome back to Calculus 3, section 12.7 on tangent planes and linear approximation. Remember the tangent lines in Calc 1? Well, this is the equivalent in Calc 3. When you have a line in 2D, you will have a tangent line over here, let's say. Sorry, I'm drawing vectors, oops. Tangent line. Why? A tangent line, and so on. And you know how to find that tangent line. The tangent line was that linearization function, which was f of a plus f prime at a times x minus a, which generated the tangent line. And what we used it for was what we called the linear approximation. If you wanted to find, let's say, a square root at 4.1, you would find the tangent line at 4, and then you would compute the 4.1 in the tangent line. That's what we used to do. And the result was close. So what tangent line is to 2D graph, that's what tangent plane is to a surface, a 3D surface. So now, if I have some kind of a 3D space, I am able to find the tangent line, the tangent plane to that surface. You ever wondered the graduation hats? No. It's a tangent plane to the brain. Unfortunately, not every student has the knowledge of that, so they just wear it. But yeah, they give it to everyone. That's, it's like that. What's that? The thing, the star for little Timmy, right? Participation. Oh, thank you. Yes, that's good. Even though if you don't know that it's a tangent plane to the surface of your head, it is a tangent plane. Now you will know that, right? And when you walk, you will be able to explain that to the person sitting next to you.
Who will not care.
Unless they're another calculus.
And then they'll really not care.
Because they will already know. Very good. So how do we find these tangent planes? Well, we know the equation of the plane, and now those a, b, and c from the normal vector, well, that's going to be our partial derivatives, fx, fy, right? So it is the cross product between the gradient and the other vector. Well, let's go step by step. I don't want to put everything at once. So we have some kind of object. Let's put elliptical paraboloid. We pick the point, and then at that point, there is a tangent plane. And that point, easy. That point is ABC. So now, what is the equation of that? So equation of the tangent plane. We are going to have partial derivative of f of x computed at ABC times x minus a plus the partial derivative at y, partial derivative in respect to y at ABC times y minus b plus partial derivative in respect to z of ABC times z minus c equal to 0. and that's the tangent plane. This is plus. It's a sloppy plus. We hopefully know what the equation of the plane is, right, with pluses. Good. So we are dotting the derivative vector with the line. Do we all recognize the equation of the line here? And here? And here? And now we have these guys that used to be the normal vector. Now they are the derivative, right? So it's a dot product between this one. All right, good. So let's see. Immediately we do the example. There's nothing special about this. It's, you know how to find partial derivatives. You just grind through it quickly. Tangent plane. Which one do you like less, e's or sines?
Fine.
Excellent. So z equals sine xy plus 2. Who?
What?
0, 5, and 2. So let's find the tangent plane for this surface. So where do we begin? The first thing is to create this f of x function, which is going to be what?
My
Sine
sine.
xy plus 2 minus z.
Oh, yeah. I don't know.
Wait, is that
Equal to 0, it's in implicit form. What happened?
I don't know.
I have a 3D point.
Oh, I know. Mm.
And all you need to do now is to find 3 partial derivatives, compute them at these values, and just plug everything in. You're done.
so 0, 5, 2 ABC?
Yep. Of course, cool. It's math. It's calculus. Hmm? I know. You are in my class. So I have the partial derivatives up. Check your partial derivatives, then compute each one at those points. And then plug everything in. But again, another efficient sneeze. Yeah, one and done, right? No, it's good.
Oh, efficient. I thought you said innocent.
Efficient, efficient. Yeah, welcome to my class. What can I say? You chose. I mean, you had plethora of other options. That's a good word, right?
I don't use the word like John uses only. And he also.
You guys are doing well. Please, the first row, that's how far it goes. Anything else is more calories used, and I have to eat more. So. Per. Now, what is this good for? It's good for linear approximations. What are the linear approximations good for? Well, they used to be good for computing values because we didn't have calculators and computers. We do now. So what is the whole idea of this? So you have a shape, and you want to compute the point right here, but it's not that convenient. So, but this point here is perfect for computation. So you find the tangent line, the tangent plane, there, and then the point that you want to compute and the tangent plane are very close together. So instead of computing your numbers in the shape, which is hard, you get to compute here. Because it's very easy to plug in, let's say, 3.2 and 1.9, where 3.2 and 1.9 not so hard to plug here. Do you get the idea? All of this was done and developed in 1800s, where calculators, believe it or not, did not exist. That's about, something like 50 years that we have. Before that, it was pure brain power. So when you want to compute something, you have to be clever about it, because you really don't want to be there sitting, figuring out, sine of 13.7 by hand for 3 hours. So linear approximation was the way to do it. Of course, it has uses today, but our algorithms now that we use in, computers far better than this and so on. So this is more like a history lecture now. When I say linearize something, I literally mean find the tangent plane and plug the point of interest in the tangent plane, right, and compute. So let's see immediately an example of that. Mark.
I remember, like, in Calc 2, we did something that kind of expanded off of linear approximations. Is that the same thing? Do you do the same thing for this? Can you do the same thing for this?
Yes, but let's keep it Calc 3.
What is that?
I know. You feel offended now that I'm not giving you a 30-minute answer, because I only have 7 minutes. Sorry. Holy nightmare, man. Give me. We are staying extra tonight just to counter you. All right, so here's a beautiful example. What's worse, ln or square roots?
Square root.
Excellent. So f of xy is equal to a square root of x squared plus y squared. And we would like to compute the function at 306 and negative 392. Negative 3.92. I know. It's amazing, right? 3.06. Does it look like anything else?
That's terrible, baby.
Then sit over there. You can tell I'm not in the greatest mood today, right? That meeting was awesome. So I'm just, this is like my therapy now. This is my therapy. And all of you are victims now. Okay, so we know how to find the tangent plane. Let's not drag this out forever. Find the partial derivatives and plug the values in. Oh, this is the two variable one. Yeah, there is no z here. Yeah, but it still can be done. No. Yeah, it's a plane. So I'm just going to give you immediately the regurgitated formula for it. So fxab x minus a plus fy computed at ab y minus b. You did not expect anything else other than this. Has to be that. And then plus f of ab. Of course. You have everything you need. So what do we do? What's fx? Exactly. You start, it's x over square root of x squared plus y, right? Squared. Awesome. The 2 is canceled, right? The 1/2 you mentioned, that cancels with the 2 from the derivative, the chain rule. Awesome. Exactly. And the other one is symmetric. You don't have to think much about it because it's symmetric. Just write it out. Now, which point are we considering?
3 and 4.
3 and -4. Yes, 3 and -4. So we are going to find the tangent plane at 3, -4, and we're going to compute our actual numbers in the tangent plane. So the tangent plane, I need to find fx at 3, -4, which is 3 divided by the square root of, this is 9/605, so 3/5. And fy 3 -4 is -4/5. So now we just write that the z is equal to fx, that's 3/5, open parenthesis, x minus a, which is x minus 3, plus, no, minus 4/5, y plus 4, and then plus f computed at ab, which is 5. There's the tangent plane. And now you plug in the values that you're actually interested in, which are, what were the values? 3.06, 3.92, thank you very much. So now I have 3/5, this is 6 over 100, minus 4/5, this is 8 over 100, plus 5. This is something that you can calculate without the calculator. You make 500 common denominator. Actually, you can at least knock it out by 2, right? Because this cancels down to 3. over 50. So 9 over 250 minus, cancel this down, 4 minus 16 over 250, and then plus 250 times 5 is 1250. This is what, -7? So 1243 over 250. So function computed at 306, comma negative 3.92 is approximately equal to 1243 over 250. It's approximately equal to that. It's not equal to that, it's about that.
Good question.
Yeah.
Can we add half of AB and get 5 there?
Half of AB.
No, F of AB. F of AB.
Oh, F of AB.
When we got 5. Why do they include? Is that like someone taking place of G or something? How is that?
You mean with this one?
Yeah, yeah.
Because it's
I know it's part of the thing, but like.
subtract. You have x minus a
Oh, God.
minus b, right? Okay, good. The initial value, and then you change it a little bit. So this is the initial value, and you change it a little bit in x and a little bit in y, and you get to that new point. That's all it is. You have to have the starting point. The same like for the 2D case. Here's the 2D case. You start here, right, at f of a, and then you change it a little bit. You start there, and you change it a little bit. That's actually what it is, except it's just written at the end, so that's why it's confusing. We'll do more problems next time. For this, thank you for your attention, and I will see you all. Wow, in 2 weeks? That is depressing.